will start our second day today. Of course, you had your first lecture from Dr. Venkat Reddy on indices which are really very closely tied to where we are heading today's, in today's discussion. But since yesterday was the inaugural day, we had some, things to catch up. Whatever is left out yesterday, I am going to start with that, but we don't need to go into the details about all these SDGs, but I just want to introduce the terms and then from global scale to India scale, how these extreme indices are looked at for a given year. I am going to actually refer to the published report that you will then be able to connect with this morning lecture, and then we will then start with the basics about hydrology to bring everybody up to speed on water cycle, water budget, energy budget. That's the plan for today. And if time permits, I will also talk about land atmospheric interactions and what goes behind these extreme events. Dr. Venkat Reddy alluded to that, suggesting that there are physical processes that are involved in this extreme events, development of extreme events, and how that is changing, especially with monsoon because of climate change. That's the kind of a wrapper or a kind of a closing conversation that we can have on this topic for today. So it's about 1 hour and 50 minutes that we can have, but we will have a break maybe roughly in the middle of this 150 minutes, 1 hour and 50 minutes lecture. Before I start this discussion, I wanted to ask you, are there any questions from the discussion that we had yesterday? I know, it's pretty basic stuff that I talked about yesterday. Was that, is there anything that comes to your mind that you want to open up the floor for discussion? Anything that you want to clarify from yesterday's discussion? Not much, right? That's okay. Is my microphone working in the last row? Can you all hear okay? Okay, good, good, okay. I have the names of you, all of you. So I would like to interact with you. It's not that I would put you on the spot by calling your name, but during the break or even when you ask some questions, tailoring to your research background or what you are really wanting to know, that will help me to understand when you are answering or asking the questions. But I will also get to know you more in person, right? So that's the objective of this whole session, interactions. Coming to the Sustainable Development Goals, this is the goal set up in 2015 for 15 years. Up to 2030. United Nations actually came up with this plan in 2015 in Paris. We talked about Paris Accord yesterday, where they wanted to cap the increase, the change in temperature increase to be capped at 1.5 degrees Celsius, if you all remember that number, right? The reason for doing that is to make sure that the planet is not going out of control when it comes to all the the inhabitants or the species or the natural systems that we have are intact. Even 1.5 threshold is kind of a modest goal, but I don't think we are anywhere close to reaching except India. I think India is really close to achieving that target, that not many countries are able to do that. But the purpose of doing that is to look at their influence on all of these 17 metrics that they are coming up with. It's basically, let's say, if I have to zoom this in, no poverty is number 1, zero hunger. This is for the global scale, for the good of the global population. They are setting this agenda. Number 3 is good health and well-being, quality education. So likewise, you have now when it comes to this particular class, there are a lot of, not all of them are connected directly to us. It's a broad area of SDG, Sustainable Development Goals, but we have a few of them that are very close to our interest. For example, clean water and sanitation is number one for us, directly connected. Sustainable cities and communities. When we are talking about extreme events, floods or droughts, particularly in cities, they are going to affect. So, number 11, and then climate action, number 13, how do they plan for mitigation? Yesterday we talked about mitigation and adaptation, right. So, number 13, life below water, that is marine life, but we are talking about sea surface temperature, how that is changing. There is some connection to monsoon, how that will bring rainfall into the land. So, there is some kind of connection. Life on land, right, that is another connection that we have. So, at least, and then public health, no hunger, no poverty, these are also connected. No hunger means, how do you connect hunger to what we are talking about here is food security. How does food security come into play for civil engineers or geoscientists or water people? We are talking about irrigation, water for agriculture, availability of plenty of water for growing crops. That is connected to producing enough food for people, so then there is no hunger, right. So, you can actually connect. So, the idea here is to then show for each of these 10 metrics yesterday we talked about. If you remember, the planet health check, what people try to do is to come up with what is the level of atmospheric carbon dioxide, right. That is number one, emissions, that we talked about, that is increasing, right. So, with this, what we call hockey stick, basically it is gradually increasing. If you just look at this plot, this ppm of CO2 in the atmosphere from 1960, Hawaii Mauna Loa site is the first place they started measuring, and now after 70 plus years, it is up to 417. Now, they are relating that to all of these SDG numbers like 13, 14, 2 and 3. These are directly connected to increased atmosphere. Enhanced greenhouse will affect ocean, will also affect climate, will affect food production, will affect air quality, that means the city quality of or number 3 that will also be affected, which is basically good health and well-being, which we are witnessing. For example, in Delhi, if air quality is bad, people are asked to stay home or work from home or closing the schools and those kinds of things, right. So, you have connection to carbon dioxide in the atmosphere. In that case, it's the smog in our place is basically because of agricultural residual burning from Punjab and Haryana that causes. That's the study that they are coming up with, but again there could be many number of reasons. But what I am trying to say is, for every metric that we talked about, people are now able to see the connection. For example, the CO2 increase is very close to your temperature increase plot. This is called a hockey stick. When somebody refers to you as hockey stick, you should remember, it's a stick that used for hockey, right, hockey game. It's the same kind of a curve that they are talking about, hockey stick graph. And then temperature, for example, from 1860, we have very limited data that we are talking about here, right. 1960 or 1880 in this case, 1860 to all the way up to 2025. Not much, right, 165, 66 years, which is absolutely not sufficient to fully understand. There was a question about, how do you know, we will come back to that discussion later again, the return period calculations and what is the, if you have only 50 years of data, how do you calculate 100-year floods or 500-year floods or 1000-year floods? People calculate all that, but it is a stochastic exercise that we will talk later. But the idea here with 150-year data, 150 plus year data, we are still looking at temperature increase, historic record of 1000-year floods. 1000-year floods you cannot calculate with 100-year floods, 100-year data. No, that is not the case. You can. It is a probabilistic approach. P is equal to 1 over T. That is the calculation for return period. And of course, you put the return period whatever way you want, and what is the probability that you get out of that is the way you calculate. But here, coming back to this discussion, this hockey stick you can see from all the models from historic times. We have kind of confirmed with observed data. So, we have confidence in these numbers, all the models are showing, I mean all the observed data and the models that are showing here are pretty comparable, right, very close. Then for the remaining time for the future that we do not have the record, sorry, I am sorry, this is also historic anyway, but for the remaining time after this historic times, we have to rely on these models, assuming that they have predicted well for the past, they might do well for the future. That is the idea behind climate model justification or verification. Coming to the next one, global mean surface temperature, that is also increasing. That is another metric that we talked about. If you remember the graph or the schematic that I showed, the second metric that we are saying is when you are talking about the health check of the planet, after CO2 increase, temperature increase was something we talked about. See here how many of these SDGs are directly connected to increased temperature. These are the processes, whether it is atmospheric process or land surface process or the physical quantity that we are talking about. In this case, increased temperature will create more evaporation. More evaporation means more water that will be lost. So, there is going to be a drought issue or water security issue. That is one box that I am talking about. Likewise, for every box that we have here, there is a physical connection to planet Earth, and how that is actually used for making policy decisions. How is it going to affect the goals that we want to achieve by 2030? We got 4 years left to achieve the goals. We have never come close to controlling the emission or controlling the increase in temperature. So, you can clearly see these goals are not going to be achieved, right. That is the overall message that you want to be looking at here. Then again, greenhouse gas, I am sorry, this is ocean heat content, that what we are talking about. Ocean, we will talk a little bit more about it later, but oceans store a lot of heat, right, and they accumulate their capacity, thermal heat capacity, holding capacity is really large compared to the atmosphere. But when they are showing some changes, that means we are talking about aggravating the conditions really fast. And when ocean heat content is increasing relatively, anywhere from the surface up to 2 kilometer below, they are talking about in the ocean. And all the changes that is happening, whether it is because of acidification or increased sea surface temperature, or all this mixing that is happening, causing biodiversity issues, fish kills, or the density difference that is creating the ocean currents to move back and forth, that will slow down the monsoon systems. They are all connected. So, these SDGs, there are at least 7 of them that we are seeing here are connected to ocean heat content. And ocean heat is increasing, sea level rise is very clear, that we have seen so far. Many coastal cities are vulnerable, and because of coastal cities and many of this infrastructure that are going to be impacted, you have more number of SDGs that are directly connected to sea level rise. Likewise, we have ocean acidification that is connected to many SDGs here. I am quickly going through, but you have these reports that will be made available for you to read for your information. You are not directly going to recreate them, but at least when you are connecting your motivation for research or justification for why climate change should be considered in your kind of analysis, you should be having some reference like this. Glacial mass balance, basically we are talking about ice caps both in Antarctic and Arctic, and also higher elevations, where we have glaciers, whether it is high latitude regions or Himalayas, you have all these glaciers that are being melted away, and that is causing a big problem for many things, right. For example, Ganges that starts in the Himalayas, because of the snow melt or the glacier, we are going to have more of those things melting faster, and that means maybe by 2100, if there is no glacier, we have to rely this perennial river. We call it perennial because in the monsoon season it gets runoff because of precipitation. In the non-monsoon season, still you see the river flowing because of the snow melt, right, that is constantly happening. So, we are not going to have that perennial systems anymore that are dependent on these glaciers. So, that is an example of how they can be connected. So, now you have all these SDGs that are directly connected to glacial mass balance. Arctic sea ice, that is not directly related to us, like I said yesterday, that is also decreasing. There are millions of kilometers, square kilometers of sea level, sea ice content is decreasing, melting. It's what is it going to do with us? It is going to melt into the sea, and it's going to create increased sea level, rise. That is a possibility. And then, of course, when the the heat systems, I mean storage that I talked about, oceans can hold more heat, and now with sea ice, it may have the reflection more for solar radiation when they come. But with ice that is gone now, you are going to see that radiation heating up the water, which will also increase the ocean heat content, or it may even create additional issues that we talked about, increased sea level rise, monsoon changes here in the tropics, sea ice extent that we talked about. And then, I mean, these are the metrics that are related to SDGs. There are other things in climate scales when we talk about. El Nino is one example. There are many of them. I do not know whether we will cover in this 10-day lecture, but if time permits, we will do that. El Nino, MJO, La Nina, and PDOs, ENSO. These are the metrics, like climate indices, similar to extreme event analysis that you did. There are ditto climate indices that are available. The only difference is whether extreme weather events are on a shorter time scale, these climate indices on a longer time scale. Okay. So, El Nino that is coming every 5 to 7 years. When it comes, because of how it happens, probably some of you might be familiar. This is South America here, right? This continent is South America. Peru is here. Sea surface temperature becomes abnormally high around December in that area, and oceanographers and people that study climate look at that sea surface temperature anomaly, they call anomaly. When that happens in December, they immediately start watching that more closely, because that has ramifications all around the world. For example, when that spreads across this Pacific, it becomes a problem for the rainfall patterns. There will be more rain in southern part, central part of the US, less rain on the northern part and in Canada. That is an example. India is not directly affected by El Nino most of the time, but South Asia, Southeast Asia and South America, South Africa is affected, and central to South America is also affected, dry conditions. Some of these places have more rainfall during El Nino years. They are able to confirm this over the number of years of record, by closely observing these patterns, monitoring sea surface temperature. There is a good level of confidence in getting these climate indices calculated by the community, scientific community, and once they are able to say that, they can even forecast for 6 months ahead of time and say what will be the precipitation, temperature conditions, or mostly precipitation they are talking about, when the El Nino scenario comes. So, that is the kind of relationship that we have. This is on top of climate change. This is not climate directly connected to climate change, but there is some connection to climate variability. We are talking about the past data, and then using that to predict for the near short term conditions up to 6 months to 9 months. Now, they are able to come up with a pretty good confidence on predictions of what is going to happen in some regions. It may be different for different locations within a region, but on a regional scale they are able to convey some of these things more clearly. This is the annual average temperature anomaly relative to 1991 through 2020 average. It is about what, 30 years Normally for statistical purposes, normal distribution. You saw the bell curve, we call bell curve, right, with tails having extremes. That is the normal distribution, and for drawing that kind of a distribution you need minimum 30-year data, right, that you all know for records. So they are using that 30-year record here to see what is the anomalous temperature for a given year. In this case they are talking about a given instant annual average temperature anomaly relative to that 30-year period. From all over the world they are seeing that you can see the warming conditions extremely high. I was just in Alaska a couple of months ago and I could see people are really witnessing Arctic ice. I will probably show some of these glaciers that I visited later. Yeah, go ahead. Yeah, right. Anomaly. What is anomaly? Basically, thank you for interrupting or asking that question because it is the benefit of the class now. Let us say you have a temperature record. I will relate to the data that we discussed previously in this class just last hour. 1 year of precipitation, right, daily data that you have, if you total them up, right, you get the total annual precipitation. Let us say for Warangal it is about 1500 millimeter that I say, right. So likewise you can calculate for every year total precipitation, right, and then for 1 year if it is 1600, the 2000, so you are going to see what is the deviation from that average number. So now you have to calculate the average first, and then for every year what is that deviation that you have, minus 50 plus 100 minus 25 plus 200, like that, right. Those are the deviations, and if we calculate the average of those deviations, that is the anomaly that I am talking about. If you calculate the average of those deviations, that becomes the anomaly. Time scale differs. I mean, if you want to calculate, say, temperature anomaly, the graph that I showed here for a given day, let us say, you now have the average on that particular day, you know what should be the temperature. Global average, I am talking about global average, or let us say 30 degrees Celsius, if it is the average temperature. For every cell you can calculate how much is the deviation that you are talking about from that 30-year average, right, and then you calculate the average of that, that becomes your anomaly map, right. I mean, if you kind of think over it, you will get it. It is not a difficult concept what I am talking, statistical exercise. Anomaly is the deviation from the average. If you calculate the long term average, that is your anomaly, deviation from the average. Okay. The precipitation map that we are seeing here, again 2024, this is the annual precipitation for 2024 expressed as percentiles of 30-year distribution. Good segue or connection to your question here. Your name please? Swami? Soumya? Oh, Satyanarayana Swami. Yeah, thank you for that question, Satyanarayana. So what I was going to relate to that question is, you have a number, global average. I mean, I think in this case they may have done a grid analysis, grid by grid precipitation analysis. For every grid you will have 30-year record, right, of historic average, and then for 2024 what is the difference from that average, right. Likewise for every grid you can calculate and then put it as a map. That is the anomaly or deviation. In percentile you can say, or in absolute number you can say. This is probably they are showing it in percentile. How do they define the percentile? Anywhere from, maybe I assume 10 to plus 10 to minus 10, whatever it is the average, and maybe 10 to 20 is dry below, and on the wet side is positive 20, and then anything above 90 percentile is very wet, or less than 10 percentile is very dry. That map, that the legend that I am talking about here. So if you then relate this to this map, these are really very dry relative to the last 30 years. So, these are very wet relative to the last 30 years. So, India is kind of mixed. I think you have wetter conditions, and that is probably the case for our conditions also for climate change. We may get more rainfall. That is a good thing for us. India might benefit, but we are also going to have more temperature increase, which may also evaporate most of it. So, we do not know exactly what the feedback cycles are. We will talk about feedbacks and physical understanding of those things. But just for grasping the bigger idea here on a global scale, you know how people are coming up with a map, fancy map. This looks fantastic for me because it gives you a good picture that rainfall alone, if you look at it, is so highly variable that you cannot make a single conclusion from this, what's going to happen overall on a global scale. So, you have to really look at the local scale impact. So, that is where our roles come into play. This kinds of map really help us understand that part. Yeah. So, now I will actually again some of these things are taken from these kinds of published report. I will speed up here a bit. This is not going to be legible or readable for you. This is a global, by region they are saying, in this case South Asia, SAS they call, and I am sorry for really having this dense map here. If you look at this legend here, they are talking about this increase is in pink color, blue or brown, decrease black color, right, and then 3 dots means high confidence, 1 dot means low or no confidence. If you look at South Asia, that is our country, India here in this case, hot extremes are increasing with reasonable confidence, 3 dots, high confidence. That is how you would interpret this. I will repeat this once again. This is the global map of the regions by letters, English alphabets they used. SAS is for, these are all in that figure captions that you can read later. South Asia is here with increased tendencies of hot extremes from climate change analysis that I am talking about is a possibility for South Asia including India with high confidence with respect to temperature. That is how you would relate. Heavy precipitation, if you come here down, yeah, we are going to have little bit more precipitation, little bit more precipitation, that is increase, right, green color that we are talking about, and South Asia, that is including India, with 1 dot, which is not highly confident, we are not sure, but it may happen. That is where the roles of modelers come into play. At the end of this class, if you are all understanding what is happening with climate change and how would you integrate them into modeling to predict exactly, you will address that question. If you can take one such question, how much of confidence that we can have or improve to have better precipitation for a continent or subcontinent like India, that is a big research question to address. So, we will talk more about research questions and how you formulate research ideas on the last day or last but one day, that is in our class also. But you can relate questions like this. How do you pick research topic? Looking at these reports and say what is exactly happening and how are they interpreting, why are they having no confidence or low confidence, can we have better analysis to improve the confidence, those kinds of things you can have. But message here is temperature is increasing, precipitation might be increasing, agricultural drought they are talking about, or ecological drought for South Asia here, it is hashed, right, there is a slanted line here, I think, maybe not, yeah, I think it is there. That means they are there, but not highly confident about what is going to happen with drought. So, that means it opens up a good question about what is going to happen to India on drought. We will talk about drought day after tomorrow, I think. Full class is on drought. So, you will fully understand how to model drought, what can we understand about drought in India and all that we will say. We will discuss in detail, but on a global scale to regional scale, when you look at, people are not sure what is going to happen here. It is a wide open field for us to think about research, right. So, it is a summary from that report that I am trying to gather. One other inequality that I talked about, I do not want to kind of be a person to criticize anybody or anything here, but what generally these reports say I am interpreting here, right. So, these are countries, each one is a country, right, dots. Many countries that are here, basically the vulnerability that we are talking about on the y axis, and emissions per capita emission. For 1.4 billion people, if you average the emissions divided by 1.4 people, our emission is really trivial, insignificant, right. That means we are one of the low emitting countries, but with high vulnerability scenario. This is true for many of these middle income or low income countries, whether it is Bangladesh or India or Sri Lanka or Maldives, they may be going underwater, or Solomon Islands, Pacific Islands. There are a lot of small islands. Tuvalu, for example, they are talking about not going to exist. They are all coming here. So, the just simple interpretation is that vulnerability is high for really lot of countries that don't even produce any emissions. Maybe rich countries, Europe or Asia, North America like US or other countries are here, high emission with less vulnerability. Per capita consumption and the emissions of all these fossil fuel related GHGs are higher for some of these advanced countries, but they are also not going to be as vulnerable as some of the other countries. That is the interpretation of this graph. Whatever it is worth, you take it. I mean, do not go into the other aspects of it in terms of policies or excuse me, policies or politics or whatnot. As a scientist, when you look at how can we change this map, what can we contribute to improve the well-being of the planet or the people, or to improve the conditions. That is probably a lifetime goal for each of us. It can be 50 years of career that we are talking about here. So, oh, that is a big question. That is the discussion they had in the COP, community of practitioners by United Nations climate change conference people last year. It did not go well. They call it damage, loss and damage. That is a compensation, that what we are talking about. They want to put it like in Paris Accord. They want to come up with an accord saying that these countries that are vulnerable should be compensated, right. So, they even created a fund called a climate fund, and they said rich countries should put money into that pot of billions of dollars, $100 billion or something they put already, but not many countries are developed countries, and it is a kind of an insurance thing, liability part, legal thing. They do not want to commit, so it did not go. US walked away, Europe probably did not commit too much, or many other countries did not show interest. So, but many other countries wanted to even have that verbiage of saying these vulnerable countries are eligible for loss and damage or something, that kind of a language they wanted to insert. But if you become one of these top notch policy makers and ambassadors of this country to represent UN, you will come to realize that how much of a difficulty it is to even put one word or one sentence that you think represents your country, because there will be a lot of push and pulls coming in the way. I do not know the latest situation of that particular loss and damage acceptance, but there is another meeting, United Nations Climate Change Conference, COP 30, number 30. There are 30 meetings that have happened in the last so many years. This year it is going to be in Brazil. Belém is the town name, Belém, Brazil. I may not be going, but I have contributed the report for that conference. I was in Paris just before coming to this one, where we talked about how Congo Basin is going to be impacted. So, we are trying to really present that report. It is not connected directly to this class, but what I am trying to say is these kinds of reports are going to be presented and discussed and debated and released for public consumption. So, we do not know where the direction will be for that particular question. Since you asked about loss and damage, I just wanted to give a broader picture about that. Yeah, yeah. Resilient infrastructure, yes, definitely it is part of adaptation strategy. So, we will talk more about that, certainly it is coming. I will talk about that in day 6 or 7, I am having all that discussion. So, quickly covering again, I think I am sorry again I am going slow. When questions are asked, I feel like answering in detail. So, that is where I think I am going slow, but I hope it is not boring for you. Please let me know if it is going slow, we can speed it up. Human systems, natural systems is the general description. When we talk about agricultural lands, it is a human system. We are modifying the landscape, irrigating the land, that is the connection that we are talking about. Ecosystems are forests that are undisturbed, pristine watersheds, and those kinds of other systems that we are, ocean species, marine species and all that. So, they classified human systems, water availability, health and well-being, cities, and then looking at for each continent which ones are vulnerable. And for example, if you look at, I am just giving one example, but you can interpret yourself later on. Physical water availability for Asia, we are going to have adverse impacts, and there is also going to be a positive impact. So, that is where we are harnessing the benefit of excessive rainfall. How I would interpret, for example, in this case, we may have more rainfall, let us say 5 or 10% more on a subcontinental scale for India. That means it is a huge source of water for us. You do not need to suffer with the drought conditions, provided we have good water management plans. If we have it, that is what the linkage is here. It is going to be adverse with excessive rainfall. You will have more rainfall, more floods possibility. We saw from previous discussion Nagavalli, Vamsadhara basins, we are studying that more intense rainfalls and flooding potential will be there. But if we have best water management strategies, minimize flooding by building structures, resilient infrastructure, we save that water, cascade of tanks in another study that Dr. Venkat Reddy was showing, increase the capacity of those structures, store more water, it supplies more water, it recharges groundwater, those kinds of things. You can make the negative into positive conditions based on how as engineers we come up with design plans, right. That is the connection. So, I am just taking one bullet to explain this, right. So, one particular row in this table. So, likewise when you have time, read each one of these variables and see where we stand, how as scientists and engineers we can come up with a plan for changing the worst condition into a best condition. Okay. I will go on with the next slide here. Yeah, this is again per capita emissions. I do not need to dwell too much into this. Global carbon emission budget that they are saying here, global scale, India is at the very low level here in this case. South Asia is the least producing GHG emissions, as you can see on the right side, and our contribution of CO2 or methane or nitrous on a global average, when you talk about the budget, is less than 9% on the total of 59 giga tons of carbon dioxide equivalent that they are talking about. India or South Asia is roughly about 8 to 9% here. So, the idea here is to get that it is not that we should be polluting more. Okay, I am not justifying that we are okay to release more CO2 or GHGs. Don't take it like that. Even with this, if we have a sustainable, if you want to have a sustainable growth, there is lot of innovation or novelty that you can bring in to sustain good quality life, to improve the planet's health, to minimize the mitigation or improve the adaptation, those kinds of things that I am talking about. So, change the opportunity into something that can really make this place better, that is the idea here. Okay. The last one on this global scale thing I will show here, if you see here, we are more vulnerable. Asia, with increased population because of sea level rise, Asia as such will have 64 million people directly on the line of fire because of sea level rise, compared to 3 lakh people in North America, for example, roughly 0.34 millions, 3.4 lakh here in this case. So, 3 lakh versus 6 crore people in Asia that will be impacted. You can see the number of people that are impacted with one variable of climate change, which is sea level rise that I am talking about. Why? In India, we have big cities, whether it is Kolkata to all the way, where you come on the east coast to Chennai, to Kochi on the west coast, to Mumbai, all of those big cities, you have millions of people that will be directly affected because of sea level rise. So likewise, you have on a global scale, if you look at, there are a lot of places, that big cities are all, if you look at top 20 cities, mostly they are all on the coast. There are more than 20 million people, if you see. They are all vulnerable. So that is the idea. And then this feedback, I will come back again. This is an interesting graph that I wanted to study or show you. This opens up a lot of questions for us, research questions for us, which we can address later. For example, I will talk in depth this one, bear with me, because it's an important exercise for us to understand the connections. Extreme heat, right, temperature increase that you calculate based on the today's afternoon session, let's say, extreme heat index, what is that, CDD, cumulative dry days, or temperature of 95 percentile exceedance of, let's say, threshold of 35 C or 40 C. You can come up with those extreme values, right, easily now. I mean, after today, let's say. You connect that to this particular map, which is what is happening with extreme heat. It will, deplete soil moisture. It will evaporate. I mean, good rain that we got 2-3 days ago, but they are going to be lost if temperature is higher, right? All these trees are really talking on a daily basis between the atmosphere and the soil. They are sucking all the moisture. They are releasing this moisture into the atmosphere, right? So that's the reason why we are losing the soil moisture. Where there is no vegetation, directly sun comes and takes that moisture, evaporation. ET, evapotranspiration from the plants and evaporation directly from the soil combined when there is extreme heat happens, we are going to be losing all the moisture, right? And of course, it's also uncomfortable. People's health is affected. Heat stroke comes, right? So that's the health part that you are seeing here, this particular box. So what happens when there is less moisture? The next one here, in the connection here, if you look at, I'm sorry if it's readable for you. It's all readable in the last row for you. Can you read it? Sorry. So maybe that's all I could see. I think this is a limitation of my slide here. Bear with me, but I think when you get the slides, you should be able to expand. And the report is also having this graph. So what I'm talking about is crop yield will be reduced because of dry conditions, right? Drought conditions. If there is drought, then there is going to be more inflation with food prices. That is the connection that we are talking about here, right? And that means farmer will get less income, reduced income in the household, right? And then you are talking about reduced labor capacity. People have to sit inside until the sun sets to go out and work. Labor efficiency is affected, or they cannot work comfortably, under heat stress conditions. Decreased quality of life that we are talking about. Increased malnutrition. When there is low food production, people cannot feed their own family or cannot supply, and famines that you are seeing in Africa or many other parts of the world because of crop yield loss, that what we are talking about. Increased malnutrition because of reduced food security. So you can see the connection. Temperature increase, right? It happens. Don't just think mechanically, okay, I'm going to calculate using my skills, writing a code in Python, Jupyter, whatever, and then downloading all these fancy data sets. You have to pour your mind into looking at what is the impact of the number that you are calculating. How can you relate to any of the science questions that we have here? See here the connections that we are talking about, any number of connections that we can establish. That is an example. Yeah, you have a question? Introduce yourself to me again. Imran, okay. Yeah.
Previously I did research I got to know that extreme heat conditions, especially the urban areas, where it is called as urban heat,
Yeah.
are directly causing flash floods.
Oh yeah, there is land atmospheric interactions. Yeah. Well,
I just want you to throw some light on how it is exactly happening.
well, actually, urban heat islands. Yeah, I mean another. relates to both land surface and also atmosphere. So, the instability in the atmosphere causing thunderstorms over the same area brings heavy rainfall events. So, the destabilization of atmosphere, if you bear with me, maybe I think we will have time to get to that point by today. I have some slides to talk about the physical process, what is happening with respect to heating, and if you can really wait until that time, and if I do not address, let us talk about it later. But it is coming, but there is a connection there between land and atmosphere, and that instability in the atmosphere bringing more rainfall when the dry air mass goes up, because the vacuum is being filled by cold air mass. But I will talk more about it later. But thanks for that question. Again, in the interest of time, I am going little bit quickly on this one and then move on. Again, this is on a broader scale, right, global scale stuff. There are 4 things that I show here. Risk of species loss on natural ecosystems. If you look at 1 degree or 1.5 degrees, 2 degree increase, 3 and 4 scenarios. Yesterday we talked about RCPs in CMIP 5, SSPs in CMIP 6, right. That is basically climate model intercomparison project CMIP. Version 5 was the last one, version 6 is currently going on. With any number of scenarios, 4 of them that we are showing here, India is really going to be having lot of issues here with respect to species losses and heat humidity related risks. You can clearly see we are having a big range, I mean 1.5 to all the way up to 5 degrees Celsius increase. India is constantly on the darker side, it is going to be more vulnerable. That is what I am saying here with future. Maize yield, another one that they are showing, it is going to be affected with different temperature increase, and India is showing some signs of stress here. Fisheries yield, we have a big coastline here, right. There are lots of fishermen community that rely on fish yield, and that is going to be affected in many countries, many regions, and including India that we are seeing. So, these are 4 metrics that they are coming up with. This is from the latest report of climate analysis, right. So, likewise they are coming up with every year. So, now I am just introducing the idea of how you can read this report and understand what is happening to India, right, and that is where it will come into play, or wherever you end up going and working, it could be another country, another region, another continent, right, but these ideas remain intact for you to understand how people are relating climate change to any number of issues that are related to what you can pursue as a research goal or a professional goal. Okay. Now, I am going to come back to some of the literature, basic things about water, why we need to consider water, and what is hydrology, climatology, hydrometeorology. I will quickly whisk through some of these things, might be relevant to your interest, and you might be familiar also already, but still for the interest of everybody's attention, I will start from this again. Water is essential for humans and for natural systems, right. We know that natural systems including biodiversity, forest loss and what not, and then natural systems that we talked about, oceans and fisheries, and humans, agriculture, cities, urban areas, all of them will be impacted. For that, water is essential. Only small portion of water is available as fresh water, right. 70%, I mean 3% is available as fresh water in the entire planet. The remaining either frozen or as sea water, right, ocean. So, that is not useful. So, with that 3% water we are talking about, how important it is for us to carefully manage it. 70% of that water is of freshwater withdrawals from lakes, rivers and groundwater is used for irrigation. That 3% fresh water that we have, that includes surface, subsurface, of which 70% is gone for irrigation. That means we are talking about the remaining 30% that is available for consumption, for humans, for cattle, animals. So, is that going to be industrial use, municipal, commercial, hydropower, all those things. So, again that is going to be a challenge for us, right. So, we have certain amount of water coming from the atmosphere, precipitation. We have certain amount of demand. If they match supply and demand, no issues. It is your monthly income budget, let us assume like that. We get certain amount of salary, if our expenses are going to be within that salary amount, you are good. Your salary is less, your expenses are more, it is deficit budget, right. We are talking about building up the deficit more and more and more. If you have more salary, less expenses, you have more savings. That is not happening for many of us, including us, right, many of us. But the same thing for happening, happening for the planet Earth. We have less supply, more demand because of population increase, because of the needs that we have, and because of dwindling supplies also to some extent. We are talking about supply becoming not equal. So now our role is to understand where we have the supply more, where we have less supplies, where we have more demand, where we have less demand, and how often we get precipitation, what is the occurrence of it, what is the magnitude of that supply, how much we need for certain sectors. That is the kind of question that we want to ask, right. Again, going back to this historic water cycle, you are all familiar with this. I am still going to repeat. It is a very active system, right. On a daily basis, if you look at this water cycle, it is the distribution of water. It is essentially water in the form of three phases, right. Ice, liquid water, and water vapor, or these three things are either staying in one place or moving around across this whole globe, on different time scales and different processes, for different processes. Water comes from the sun, evaporates and goes as clouds, and then comes precipitation again. Water comes as precipitation, runs on the ground as runoff, and then gets into the groundwater, and then part of it is ending up in the ocean, part of it is ending up in the groundwater system. So how do you quantify this is a question that we are asking. It is changing on a global scale, it is changing at your watershed scale. It is changing from one year to the next year. It is also changing because of the changes we bring to the system, meaning we cut down the forest, we build a lot of lands, we remove the lakes, we do not harvest the water. So we have lots of modifications to this water cycle, right, and that is actually causing a problem. And I think I will come back to that also later. There is a slide that shows this water cycle is not valid anymore. The water cycle that we have seen from our school days is gone. It is now needed to be adjusted for all these anthropogenic, meaning human induced changes to the system is being now looked at. Hydrology, as we all know, is one of the fascinating fields, right, because it touches on so many important things. Let us look at one by one. This definition is somewhat very interesting. They talk about occurrence and movement of water. Occurrence means where you get the rainfall and how much you receive it, right, and how it is moving from one place to the other, right, and then on the land, meaning it can go as a river, it can also go to the groundwater, that is the underground part, and then it could be having both chemical and physical properties. What is the pH of that, what is the pollution level that we are talking about in those quantities, what is the E. coli that you have in the water body, and then what is it related to biotic and abiotic environmental components, both in the natural systems and human systems, and then what will be the effect on humans of that water. So there are a lot of connections that are leading to this science that talks about water, that relates to water, is the field of hydrology. So it is a fascinating field. Everything under that water umbrella comes under hydrology, right. But still we are, most of the time as hydrologists, we relate this to land surface part most of the time, and emphasizes on the land phase of the hydrologic cycle, but it connects to many disciplines: biology, chemistry, ecology, mathematics and physics. And then when we talk about water, many times we need to be thinking about what watershed we live in. Okay? How many of you know the watershed that you live in your own place? I know you are coming from different places. Does anybody tell me what watershed that you come from right now? I mean, don't tell the big name, like if you are from UP, and don't tell I am from Ganges Basin. That's pretty obvious, right? Mahanadi or Krishna, Godavari, you can easily say. But I am saying at the watershed means it's a smaller unit. So you may not know that, right? Go back to your place. Go back to your place after this class and ask this question yourself. What's your watershed? Right? That is the starting point for you to relate as a scientist to what you are looking at. You may not be studying that watershed, but I am saying on a daily basis when you see some floods or drought news, then you can relate to real world situations. Okay? And then of course, water flows through these valleys and stream network. Climatology is another connection that we have, which is basically applied science that examines the fluxes of three things: energy, mass and momentum. If you remember these three things that moves between land, ocean surfaces and atmosphere. Let's break that down a little further. If anybody can tell me what energy is, that would help. Can somebody tell me what is energy when we talk about energy in this case? Yeah, solar, right, or the energy that we get from the sun, how it's being used for heating up the atmosphere or water, and how the whole energy budget is managed. That is related to climatology. Mass, what is mass? Water, primarily water in this case. Air mass is also included, but water, when you talk about how much is the mass, how much is the precipitation, how much is the volume of water that you have on the ground, how it's divided between different components, water cycle that we talked about, right? So energy, that is divided from the solar energy into different components, mass, and then what is momentum? Sorry? Right, it is a movement with energy. Anything that has weight attached to that, when it moves, it's a momentum, right? Right, it's basically water when it moves with a force, it's a momentum. Water vapor in the atmosphere, when it moves, it is a momentum. The circulation, atmospheric circulation that we are talking about is because of the rotation of the earth, and also it's because of the motion that we are talking about from both water, water vapor and air, right? So these three things we are talking about: water, energy, mass and momentum. These three things are constantly changing over place and time. That is looked at in the field of climatology. Climatology connects a longer time scale. So that's a very big area, right? And then vertical and horizontal fluxes of mass. So now we are talking about not just flowing in horizontal direction. Circulation, when you talk about, it has, wind speed, when we talk about, there is a direction associated with wind. It can come horizontally, it can also move vertically, right? Likewise, water, horizontal, water can percolate vertically down. So we are talking about horizontal movement of fluxes, vertical movement of fluxes. That is also being dealt both on the land and in the ocean and atmosphere. There is also seasonal variation, the circulation that we talked about just now. And then atmospheric phase of hydrologic cycle is a climate related phenomena. Basically, hydrologic cycle has both surface connection and the atmospheric connection. There are three components that I will come to. So for now, just hold your thought on hydrologic cycle. Means it does not mean that there is only one hydrologic cycle. There is a hydrologic cycle connected to land and connected to atmosphere. Climatology, people are talking about atmospheric part of hydrologic cycle. Computational resource is very important for modern climatology, since simulation is involved for a longer time period. Whenever we talk about climate cycle, it's basically a bigger time step, right? Larger time step. So now the whole planet is divided like this, right? As you can see here, I don't know whether it's visible, but if you look at closely, these are grids, right? You have horizontal grids. Every land parcel, every land mass is basically divided into grids. And we are talking about real shallow atmosphere of 50 kilometers from the land surface. From the surface all the way up to 50 kilometers is really skinny, very small portion compared to the real all 5 layers of atmosphere, right? We are talking about, stratosphere to all the way up to toposphere to troposphere up to mesosphere and beyond. There are 5 of them. So, we do not model anything below or beyond 50 kilometers, let us say, and flights go roughly about 40,000 feet or 13 kilometers, 14 kilometers high maximum, that is all. But now, we want to understand these vertical horizontal motions of fluxes, mass, energy and momentum that we talked about in climatology for all these grids, both horizontally and vertically. If you can build a model that does all this, that becomes your climate model. That is what people are doing. So, there are different models that people talk about. So, there are equations, the physical processes that we are talking about, whether it is precipitation, humidity, temperature and wind speed, what not, and the radiation budget, energy budget, all of those things are calculated for every grid on the horizontal scale and on the vertical scale, and put together how one grid is allowing that flux to move to the next grid, how it is moving vertically up and down for every time step, for every day, for every month, every year, multiple years they calculate. So, that becomes your climate model projections over a longer time. So, that is the whole process. I mean, it is not difficult to understand, you probably have an idea, but climate model simulations are done at that highest level. If you break that down, these grids into smaller units, now that is the idea. 20 years ago, 30 years ago, they started with 2 degree pixels, meaning that box that I am showing here was 2 degree by 2 degree, roughly about 200 kilometer by 200 kilometer on the equatorial region. Maybe in the northern southern hemisphere it gets stretched a bit, okay, different sizes, but on an average 200 kilometer by 200 kilometer is one box. Now, over time they have reduced that box from 200 kilometer to 100, 50, 25, 10 kilometer. Right now they are breaking these cells into 10 kilometer or even less, all the way for the whole globe. You can see the computational demand that it adds up for every pixel when they break it down to 10 kilometer to simulate these fluxes for every minute in some cases. If they want to really understand the cyclones or tropical cyclones or hurricanes or floods or droughts, there are many things, right, instantaneous landslides. So, you need high resolution data. So, reliable data that simulates very well considering all these processes with good data, right. So, it is a huge enterprise. We do not have a climate model currently that can do a very good job focused on India. Maybe they are coming up with one, I think, as I speak, or maybe already it is out, I do not know that, but I am just saying there are so many other models on a global scale from other parts of the world, but there is such a huge demand here to come up with a model that accommodates all this. We have the capacity, you have the capacity, but we need the kind of the motivation, the resources to come up with a plan, resources and opportunities to really put together this piece and to come up with a fancy model that can do a wonderful job, fantastic job for India or for the region, for the globe. So, hydrometeorology, what is the difference? I mean, so now I combine hydrology and climatology, that is as one discipline, and hydrometeorology, which is another field, which is basically we are talking about the mean conditions. What is the mean? The average, right? We are talking about 30-day average, 1 year average, whatever, or the higher order moments. It could be standard deviation or variance, higher moments of statistics of the atmosphere that is represented, whether it is for precipitation or a temperature or other variables on different time steps like daily, monthly, annual scales. That is the traditional way of thinking, that is actually hydroclimatology or climatology. But now people are saying no, when we are talking about average conditions over a long time, that is climate, it is not meteorology. So, then what is meteorology? They want to combine hydrology and meteorology over a shorter time scale, right. So, that is the difference between hydrology hydroclimatology and hydrometeorology. Coming to modern climate system, we are dealing with this planet Earth at 5 spheres. For 5 spheres, there are this energy, mass and momentum that is moving across this whole globe, considering atmosphere, cryosphere, lithosphere, biosphere and hydrosphere. These are 5 spheres that we need to understand. We are connected to hydrosphere, atmosphere, but we are not so closely connected to cryosphere. But lithosphere means, I'll have to explain one by one, right? Atmosphere we know, anywhere from surface to up to 50 kilometers. Cryosphere, these global Arctic masses, ice mass, glacier mass, those are cryospheres. Lithosphere is the soil below up to 2 kilometers. Biosphere is vegetation that we have on the ground. Hydrosphere, anything related to water, the river, lakes, ocean, all of those things are connected to hydrosphere, right? So these 5 spheres are constantly linked up in climatology. But in hydrometeorology, basically we are talking about the relationship between the atmosphere and the land phase of water, very closely connected to atmosphere and land surface of water, land phase of water. According to NOAA's 1996 definition, but the distinguishing thing about hydrologic cycle is this. When we talk about hydrology or terrestrial hydrologic cycle, 3 things that I talked about: inflow, outflow and storage, right? So what is inflow in this case? Whatever we get, and whatever we let go is the outflow, and whatever is remaining in the area is the amount of storage, right? Whether it is in the land or in the ocean. In the atmospheric bank, that is for the land surface part. For the atmospheric branch of hydrologic cycle, we are talking about precipitation coming from the sky, evaporation and the atmospheric transport of water, right? That is the atmospheric hydrologic cycle. So you can clearly see the connection there. So precipitation, right, is the kind of inflow, outflow is your evaporation, and transport or storage. Atmosphere doesn't store, it's basically transport from one place to the other. Cloud moves, water vapor moves, all of those things, right? So that is the storage in the land surface, but transport of water in the atmospheric side, right? But there is one connection between terrestrial branch of hydrologic cycle and atmospheric branch of hydrologic cycle, which is water. Where is that water coming from? Evapotranspiration, ET, right? So whatever we have on the ground as vegetation, right, they are supplying water to the atmosphere as evapotranspiration. So the loss for the land surface as ET becomes the gain for the atmosphere, because they get that water from the land to the atmosphere. And what is the loss for atmosphere in this case? Can somebody tell me? This is the quiz. I talked about the loss for the land surface because of evapotranspiration. What is the loss for atmosphere? Very good. Precipitation. I am glad that you are with me. So that is actually losing that water to the land surface. So that is the loss for atmosphere. So that loss, and if you ask an atmospheric scientist, they will say precipitation is a loss for us. But for hydrologists, the life starts from precipitation, because that is the source of life, that is the source of input for us. So depending on the discipline, you can see one calls as a loss, one calls it as a gain. That's an interesting thing to observe here, right? So now quickly, 2 climates that we are talking about. In the past, people are talking about climate is the dominant one. They ignored the land mass, right? They talked about anybody pre-1960s, if you go, they will say, oh, this planet is relying to only based on the atmospheric conditions, we need to decide everything. But people on the other spectrum, the climate of the second kind, said no, just don't talk only about atmosphere, you have to include the land surface also as part of it, because now you saw the connection, right? What we are losing from the land is the gain for the atmosphere as input. So what they lose is the gain for the land. So there is that connection that we already have. So this is the new kind of climate that we should be considering as climate of the second kind. Climate of the first kind, people always close minded, thinking only about atmosphere, but climate of the second kind said we have to be little more broader, combining both land and atmosphere. That's how the field of hydrometeorology and the connections between land and atmosphere that came together in the post 1960s and post 1970. That is the end of it. I will stop there for questions, and then maybe we can have a 5-minute break, and then I will continue on with the next interesting part. Any questions that you have on those? This will go really quick. The next, both on the land and in the ocean and atmosphere. There is also seasonal variation, the circulation that we talked about just now. And then atmospheric phase of hydrologic cycle is a climate related phenomena. Basically, hydrologic cycle has both surface connection and the atmospheric connection. There is there are 3 components that I will come to. So for now, just hold your thought on hydrologic cycle. Means it does not mean that there is only one hydrologic cycle. There is a hydrologic cycle connected to land and connected to atmosphere. Climatology, people are talking about atmospheric part of hydrologic cycle. Computational resource is very important for modern climatology, since simulation is involved for a longer time period. Whenever we talk about climate cycle, it's basically a bigger time step, right, larger time step. So now the whole planet is divided like this, right, as you can see here. I don't know whether it's visible, but if you look at closely, these are grids, right. You have horizontal grids. Every land parcel, every land mass is basically divided into grids, and we are talking about real shallow atmosphere of 50 kilometers from the land surface. From the surface all the way up to 50 kilometers is really skinny, very small portion compared to the real all 5 layers of atmosphere, right. We are talking about stratosphere to all the way up to toposphere, to troposphere, up to mesosphere, and beyond. There are 5 of them. So we don't model anything below or beyond 50 kilometers, let's say, and flights go roughly about 40,000 feet or 13 kilometers, 14 kilometers high maximum, that's all. But now we want to understand these vertical, horizontal motions of fluxes, mass, energy and momentum that we talked about in climatology for all these grids, both horizontally and vertically. If you can build a model that does all this, that becomes your climate model. That's what people are doing. So there are different models that people talk about. So there are equations, the physical processes that we are talking about, whether it is precipitation, humidity, temperature, and wind speed, whatnot, and the radiation budget, energy budget, all of those things are calculated for every grid on the horizontal scale and on the vertical scale, and put together how one grid is allowing that flux to move to the next grid, how it's moving vertically up and down. For every time step, for every day, for every month, every year, multiple years, they calculate. So that becomes your climate model projections over a longer time. So that's the whole process. I mean, it's not difficult to understand. You probably have an idea, but climate model simulations are done at that highest level. If you break that down, these grids, into smaller units, now that is the idea. 20 years ago, 30 years ago, they started with 2 degree pixels, meaning that box that I am showing here was 2 degree by 2 degree, roughly about 200 kilometer by 200 kilometer on the equatorial region. Maybe in the northern southern hemisphere it gets stretched a bit, okay, different sizes, but on an average 200 kilometer by 200 kilometer is one box. Now over time they have reduced that box from 200 kilometer to 100, 50, 25, 10 kilometer. Right now they are breaking these cells into 10 kilometer or even less, all the way for the whole globe. You can see the computational demand that it adds up for every pixel. When they break it down, to 10 kilometer to simulate these fluxes for every minute in some cases. If they want to really understand the cyclones or tropical cyclones or hurricanes or floods or droughts, there are many things, right, instantaneous landslides. So you need high resolution data. So reliable data that simulates very well considering all these processes with good data, right. So it's a huge enterprise. We don't have a climate model currently that can do a very good job focused on India. Maybe they are coming up with one, I think, as I speak, or maybe already it's out. I don't know that, but I'm just saying there are so many other models on a global scale from other parts of the world, but there is such a huge demand here to come up with a model that accommodates all this. We have the capacity, you have the capacity, but we need the kind of the motivation, the resources to come up with a plan, resources and opportunities to really put together this piece and to come up with a fancy model that can do a wonderful job, fantastic job for India or for the region, for the globe. So hydrometeorology, what is the difference? I mean, so now I combine hydrology and climatology, that is as one discipline, and hydrometeorology, which is another field, which is basically we are talking about the mean conditions. What is the mean? The average, right? We are talking about 30-day average, 1 year average, whatever, or the higher order moments. It could be standard deviation or variance, higher moments of statistics of the atmosphere that is represented, whether it's for precipitation or a temperature or other variables on different time steps like daily, monthly, annual scales. That is the traditional way of thinking. That is actually hydroclimatology or climatology. But now people are saying, no, when we are talking about average conditions over a long time, that is climate, it's not meteorology. So then what is meteorology? They want to combine hydrology and meteorology over a shorter time scale, right. So that is the difference between hydrology, hydroclimatology and hydrometeorology. Coming to modern climate system, we are dealing with this planet Earth at 5 spheres. For 5 spheres, there are this energy, mass and momentum that is moving across this whole globe, considering atmosphere, cryosphere, lithosphere, biosphere and hydrosphere. These are 5 spheres that we need to understand. We are connected to hydrosphere, atmosphere, but we are not so closely connected to cryosphere. But lithosphere means, I'll have to explain one by one, right. Atmosphere we know, anywhere from surface to up to 50 kilometers. Cryosphere, this global Arctic masses, ice mass, glacier mass, those are cryospheres. Lithosphere is the soil below up to 2 kilometers. Biosphere is vegetation that we have on the ground. Hydrosphere, anything related to water, the river, lakes, ocean, all of those things are connected to hydrosphere, right. So these 5 spheres are constantly linked up in climatology, but in hydrometeorology, basically we are talking about the relationship between the atmosphere and the land phase of water, very closely connected to atmosphere and land surface of water, land phase of water. According to NOAA's 1996 definition, but the distinguishing thing about hydrologic cycle is this. When we talk about hydrology or terrestrial hydrologic cycle, 3 things that I talked about: inflow, outflow and storage, right. So what is inflow in this case? Whatever we get, and whatever we let go is the outflow, and whatever is remaining in the area is the amount of storage, right, whether it is in the land or in the ocean. In the atmospheric bank, that is for the land surface part. For the atmospheric branch of hydrologic cycle, we are talking about precipitation coming from the sky, evaporation and the atmospheric transport of water, right. That is the atmospheric hydrologic cycle. So you can clearly see the connection there. So precipitation, right, is the kind of inflow, outflow is your evaporation, and transport or storage. Atmosphere doesn't store, it's basically transport from one place to the other cloud moves, water vapor moves, all of those things, right. So, that is the storage in the land surface, the transport of water in the atmospheric side, right. But there is one connection between terrestrial branch of hydrologic cycle and atmospheric branch of hydrologic cycle, which is water. Where is that water coming from? Evapotranspiration, ET, right. So, whatever we have on the ground as vegetation, right, they are supplying water to the atmosphere as evapotranspiration. So, the loss for the land surface as ET becomes the gain for the atmosphere, because they get that water from the land to the atmosphere. And what is the loss for atmosphere in this case? Can somebody tell me? This is the quiz. I talked about the loss for the land surface because of evapotranspiration. What is the loss for atmosphere? Very good, precipitation. I am glad that you are with me. So, that is actually losing that water to the land surface. So, that is the loss for atmosphere. So, that loss, and I mean, if you ask an atmospheric scientist, they will say precipitation is a loss for us. But for hydrologists, the life starts from precipitation, because that is the source of life, that is the source of input for us. So, depending on the discipline, you can see one calls as a loss, one calls it as a gain. That is an interesting thing to observe here, right. So, now quickly, two climates that we are talking about. In the past, people are talking about climate is the dominant one. They ignored the land mass, right. They talked about anybody pre 1960s, if you go, they will say, oh, this planet is relying to only based on the atmospheric conditions, we need to decide everything. But people on the other spectrum, the climate of the second kind, said no, just do not talk only about atmosphere, you have to include the land surface also as part of it, because now you saw the connection, right. What we are losing from the land is the gain for the atmosphere as input. So, what they lose is the gain for the land. So, there is that connection that we already have. So, this is the new kind of climate that we should be considering as climate of the second kind. Climate of the first kind, people always close minded, thinking only about atmosphere, but climate of the second kind said we have to be little more broader, combining both land and atmosphere. That is how the field of hydrometeorology and the connections between land and atmosphere that came together in the post 1960s and post 1970. That is the end of it. I will stop there for questions, and then maybe we can have a 5-minute break, and then I will continue on with the next interesting part. Any questions that you have on those? This will go really quick. The next, really a good connection to your afternoon session and what we talked about in the morning also. Couple of papers I am presenting or showing here, not to discuss in detail, but for you to probably read for your interest if you have time. Later on, download, keep them, or if you need them, send me an email, I will send the PDF for you. One is, these are the hard working students, from IIT Kharagpur and other institutions have performed over the years that I was fortunate to be part of, and I am presenting here. It connects to these extreme events, that is why I wanted to bring this. So, I do not want to repeat too much because it is already a published work, but it might give you an idea. You remember this morning we talked about extreme events, right, where we divide this country into multiple regions, right. Here we are talking about, I do not know, it's west central to peninsular India here to northwest, central northwest, northeast, right, like that, different regions, and you can see big cities. There are 19 cities or so that we looked at, and then Z values from Mann-Kendall test that we are talking about here. We have annual rainfall, monsoonal rainfall, 1-day maximum rainfall, 10-day maximum rainfall, all these indices that you just talked about this morning, right. And this paper we looked at some 7-8 years ago for different cities, Kochi, Coimbatore, Kozhikode, Bangalore, Hyderabad, Pune, Mumbai, Surat, Nagpur, Kolkata, Indore, Ahmedabad, Bhopal, Patna, Kanpur, Lucknow, Jaipur, Delhi, and I think Ghaziabad. So those are the 19 cities we looked at, and we come up with what kind of trend that we have, increasing or decreasing trend with respect to annual rainfall or monsoon rainfall or 1 day or 10-day kind of rainfall. There is kind of a mixed signal that we got, but many cities are looking at increased 1-day rainfall or 10-day maximum rainfall, and there is also some cities that are showing decreasing monsoon rainfall, and many cities are showing decreasing annual rainfall also. So it's a puzzle, right? We don't know what's going to happen in your own town, in your own city, and we want to constantly evaluate. This was using the historic data from IMD, Indian Meteorological data for 1901 to 2015, basically about 115 years of record that we have. We calculated all these metrics and we came up with this analysis by cities as well as by basins. And the red color, actually what you see as increasing tendencies and decreasing tendencies as green color between 1901 to 2015, and then we divide. You remember I talked yesterday about pre-industrial, post-industrial. I mean, there is some level of arbitrary nature there for dividing this time zone, but looking at pre and post-industrial, let us say 1970 and after in the last case, more of red extreme precipitation that we are seeing here magnitude wise, and this is 95 percentile and the other one is 99th percentile. You can see most of the country is red in color, meaning increasing extreme events of 99 percentile, the tail that we talked about today. That is what I am trying to connect here. This was done on a larger scale for India, and we are clearly looking at based on the historic record. If somebody questions what is the integrity of this analysis or models, we are not using the model. This is reanalyzed or reanalysis data or remapped data of IMD's point data, gridded data that we talked about this morning, Dr. Venkat Reddy presented. But then we looked at the basins. There are about 23 basins or more that we looked at, and we found out consistently 99th percentile extreme precipitation events over the last 115 years have gone up. That is worrisome. That is the reason why we are having this class, to look at how can we then understand the impact of this extreme rainfall, what can we do about it, or how can we improve this analysis even to better predict into the future of all these extreme events, right. So there is a connection there. One other add on to this kind of extreme analysis is drought. This is a separate paper that we did, but it includes both the past conditions and also the future. Now you got a taste of climate models, right? We talked about climate models. This used, I think, even CMIP previous generation data set, version 3, I guess, or RCP, that is CMIP 5 versions that we used here. Historic is here. We remember that same timeline that we talked about, 1976 to 2005, and both for IMD as well as the forecast or reanalysis data that we used. So the other thing is, for the climate models, RCP 4.5, we used RCP 8.5. That is the middle ground scenario and the extreme scenario. Yesterday map that you remember, if you remember the discussion that we had. And if you look at first 30 years, or between 2030 to 2040, 2010 to 2040, 40 to 70, 70 to 2100. This is basically the duration. We are talking about months of drought conditions that are prevailing in North India, Central India, Western India. The number of months from 3.5 to 4 months are increasing. That is a huge number. 3-4 months of drought for a bigger area like India, it can create lots of problems, right? I mean, if it really happens. So that's where, I mean, this is done with the previous generation data set, but there can be newer analysis that can really tell you more or improve these results to understand better. If you go further down RCP 85, the worst case scenario, lots of red, lots of intense color here. So that's the part that people, policymakers, managers should be considering. One is the duration, the other one is the occurrence. What is the occurrence? How many events that you will see between those times? You remember we talked about CDD as an example. How many dry days, consecutive dry days that we have for a given number of events. So we talked about 10 or 13, 20 events that we are seeing. So here in this case, one such example is about 160 events that you will see for RCPs, 4, 5 into the future, 30-year time frame. More number of events that you will have. It could be shorter events, it could be longer events. I mean, when we talk about drought, there are varieties of droughts. Meteorological drought is anywhere from few days because of lack of rainfall. We are talking about 3, 5, 7-day drought, 10-day drought, maximum 1 month. But when we are exceeding to agricultural drought, I mean going to the agricultural drought period, which is about the growing season time, 3 months, 4 months time period. And then hydrological drought, which is probably even multiple months or even years because of stream flow that we are talking about used for drought predictions in hydrological drought. So here the events that we are talking about is meteorological drought, if I remember correct. 160 such events are happening in the highest level here for worst case scenario in the future. So that's a worrisome condition for us to consider, how can we do better with respect to predicting and understanding and in implementing some adaptation strategies for water management. So again the same thing, extreme events 95 percentile, 99 percentile for magnitude as well as number of events. Red events that you see here for 99 percentile, almost the entire country except the upper parts of Godavari you can see, and the southern tip is having some declining trend, but most of the country is red. That's another interesting dynamic here to look at. This is based on the historic times, right? This is observed data, not models. So there is more reliability, there is more confidence in these things. And then in the future, again you can calculate this maximum rainfall 1, 2, 3 and 5 day, for different windows, again the whole period or the first period and then the second, maybe this is a whole period, first and second period, and you can see mostly they are all showing increasing rainfall, maximum rainfall of daily. That means we are talking about more floods in cities, more floods in areas that are already developed, that will have less chances for holding this water. That's causing more problem. I mean, rainfall is one thing, but flooding, when we talk about how we modified the landscape, is also adding problems to that, right? That's adding impervious areas, minimizing the time for percolation, allowing quick runoff, flash floods happening, and the elevation of the city that changed because of constructions and everything, that can also have additional effects. That will come into more on the hydraulics and flood side of modeling side, but precipitation as an input, if you look at the increasing trends of daily maximum rainfalls in the future, or this is for the past conditions, but the trend that we are looking at into the future also is more, which may be a problem. These are the papers that you can refer to, download them later and read for your interest. And again, I am going to actually show this report, which I liked very much, which talks about just the 9 months of 2023 from Center for Environment in Delhi. They came up with down to earth report, which is wonderful. I mean, they start talking about defining extreme events. Somebody asked about how do we define an extreme event, or whether or not this event is related to extreme event or not, those kinds of questions that we asked. But they actually adopted a definition aligning with Indian Meteorological Department There is not a single definition, but there are classifications and thresholds published by IMD. What are those classifications? We are talking about extreme events. In this case are selected by IMD and CES in this case. Lightning, heavy rainfall, heat waves, cold waves, snowfall, cloudburst and cyclones, and others they call some other stuff. So lightning kills a lot of people. I would call the time scale here anywhere from few minutes, few seconds, few minutes to few days, not more than that. All these extreme events that they are bracketing. So extreme rainfall, if you look at, they call anywhere from 64.5 millimeters to 115.5 in 24 hours, which is roughly about what, 2 inches, 2.1, 2.2 inches to 4.2 inches, which is basically within 24 hours going to be a good amount of rainfall for these developed areas to follow. Very heavy rainfall anywhere from 115 to 204, and extremely heavy rainfall of 204. You are seeing that during this monsoon season, whether it is Hyderabad or Mumbai or many other cities in the middle, we are talking about extreme rainfalls of greater than 200 millimeters, right. We do not have opportunity to store them, to allow them to percolate, and they runs off on this impervious land and creates lots of flooding issues. So that's the kind of scale they are using here, called extreme weather events, EWEs. Heat waves, anywhere departure of 4.5 to 6.4 from the normal maximum temperature, and severe ones would be more than 6.4. And cold waves or cold days, they call temperature drop of 4.5 to 6.4. Cold is greater than, severe cold is greater than 6.4, mostly applies to North India in this case, North and Northeast India. Cold wave, minimum temperature drop of 4.5 to 6.4. Cold wave, severe cold wave would be greater than 6.4. Snowfall again confines to 3 states in India, Jammu Kashmir, Himachal Pradesh and Uttarakhand to some extent, but not many other states. So, and again they do not call it extreme events unless there is no death, unless there is death. Cloudbursts are happening in Uttarakhand and Himachal Pradesh and some extent in Jammu Kashmir. Cyclones, there are events that we are connected to in this region and many other parts also in western coast. Anti-clockwise mostly in northern hemisphere because of the rotation of the earth, Coriolis effect. Here we are talking about clockwise direction, and I will talk a little bit about the speed of the cyclonic twist that we are seeing is changing because of climate change for India, and how it is changing the rainfall later. I will come back to that later. But these are the extreme events. What do you miss here? Can somebody tell me? I just wanted to ask a quick question. On these extreme events, we talked about some other events also, but one thing that is missing here based on the CES definition. What extreme event is missing? Droughts. Very good. Good catch. Why is that missing? Is that not an extreme event? I just talked about previously in one of the slides that for India we did the drought analysis. Why is that not considered as an extreme event? Right. That's the reason. The time scale, I think, the logic is not clear to me here. They are considering anywhere from few seconds lightning to few hours to few days, not more than that. But drought starts from short term of drought, meteorological drought, few days. It can come in extreme events. That is what we studied before, and it can actually extend beyond few days to few months, right. The occurrence or duration that I talked about going up to 4 months, right. So, it is kind of that blurring line between calling it as an event versus a disaster. So, I think there is that fine line that they are thinking, or I am not sure that can be considered like that. A disaster means probably landslide is also a disaster, but it is included in this extreme rainfall. Anything that exceeds certain amount of rainfall, they say landslides are possible, but droughts are not called as an event, which may change over time, but something to think about in the future. So, again the rest of them are extracted from the report. In the interest of time, I am going to skip all this because you can read yourself. You know, most of the region in India are seeing extreme events, and within these 365 days of the report in 2023, they found 318 days on an average. You are getting one event or more in any part of India. So, that is an interesting statistic to me. You know, I feel like it is an important number, and then 300 or 3,300 people are dying because of these fatalities every year. That is a big number. You know, as engineers and scientists, we have the responsibility to minimize that loss or make it to zero. How is that possible? That is where early warning systems comes in, infrastructure comes in, resilience infrastructure, to understanding and you know, coming up with better tools to predict floods or droughts. All of those things combined minimizes the loss of people and also properties, livestock and infrastructure and so on so forth, right. So, there is a connection to all these things, but this is an interesting slide that I wanted to discuss. It is not from me, I show the source here, but what you want to understand from here is this, the land surface atmosphere link and the feedback that we are talking about. Somebody asked this question, so I ask you to wait, Satyanarayan Swami. So, we can see here present condition, what we are looking at is the cycle, water cycle or whatever you call that loop. You know, here evaporation, right, it happens and it brings moisture. The circulation, actually this is atmospheric circulation, evaporation that actually moves to the land, brings precipitation, and land mass is warmer because of the land, I mean the solar heating conditions, it really warms up the surface, right. So, that is today's condition. Today or this season or last season or probably next season, you are seeing like this, present day. But what is happening in the future? You have weaker circulation. On a global scale, the whole movement of mass, energy and momentum that we talked about before, causing the circulation is weakening for some reason, which we need to really verify for India whether or not that is the case, but many reports suggest that it may be the case. If that happens, added to that you have increased heating both from the sun, from for warmer land, as well as increased air temperature causing more moisture evaporation from the ocean surface, brings more moisture. That means we are talking about more rainfall. So, there is a connection to climate as well as climate variability as well as climate change in this particular slide, past and future, but this is the future here, right. So, we are expecting more rainfall just during the monsoon season, and India maybe more than 70% of the land mass gets rainfall from these monsoons, whether it is southwest monsoon or from the northeast monsoon. The periods you are familiar, right. The southwest monsoon is from, what is the period? Can somebody tell me? June to September. What is the northeast monsoon cycle? October to December or probably end of November, whatever, that 3 months roughly about. So, except coastal southern part of India, many regions are benefited by southwest monsoon, the other regions are benefited by northeast monsoon, right. So, these are the two different systems that bring, and both are really coming, are having the circulations impacted by this climate change, and that is going to really add to already created warming conditions in the atmosphere. We are not talking about the warming conditions on the land here. So, what happens to the increased temperature from these vegetation, biosphere under changing conditions? There will be more ET, right. If you have enough rainfall from here, from these monsoons, we are talking about more evapotranspiration and evaporation from the land mass that will probably give more rainfall. So, the urban heat island effect, that what we talked about before, the heat mass that goes up, and then we have all this moisture that's moving in, bringing and dumping this rainfall. One other understanding from all these climate change studies is that because of increased temperature in the atmosphere can hold up to 6 times more moisture of this movement from the ocean as well as evapotranspiration that we are having. So, the drier column in the atmosphere is more, that means they can accumulate more moisture, and then when they move to a certain place where the condensation can happen, it dumps all that 6 times fold increased rainfall amount. That's what we are talking about. So, that is why we are talking about floods that is happening from the atmospheric side. But if the land mass is not really disturbed by the humans with all these built up structures and all that, we are talking about damage to an extent, but not to a great extent. But cities are flooded because we are already changing the landscape, that is causing the problem. So, this is the connection that I am talking about between both land and atmosphere as well as climate change, and also looking at how the atmosphere holding extra moisture is dumping this rainfall. So, these are the physical reasoning behind what we are looking at as extreme events. The red maps that I showed before for the past times and also into the future is the combination of all of these physical processes that is happening over the land mass in India or probably in other parts of the world. So, again, we are expecting for India to be having at least about 5 to 10% increase. That is a big number when we are talking about during the monsoon season, about 850 millimeters of rainfall that we are seeing as an increase, right. So, that is a big number, and the variability is also there. When you consider both variability as well as the increasing trend of 10%, it is a big number. It can impact agriculture, especially if it floods. I do not know if you remember, recently I saw some of these paddy fields in India, whether it is Tamil Nadu or central India, I forget, but the farmers were impacted because of heavy rainfall during the monsoon season that flooded their crops. So, that is probably is going to happen. It is not just the urban areas that will be flooded in the future, but if it floods even the agricultural areas, food security becomes an issue. Now, you can relate SDGs to temperature increase, to extreme events, to flood, and then producing less food, crop yield is affected, hunger, which is your SDG 2, zero hunger, that is going to be not met by 2030. So, you see how the connection is established with one particular event, one particular variable, with all the global things that we are talking about here. So, that is the kind of connection you should all establish. Anyway, now coming to this regional analysis, this report again you can read later, but they divide by region, the whole country, and then they talk about how many events that all the 9 or 7 events that we talked about, they are coming up with the numbers, and then how many events on a daily scale, whether it is heat wave or cyclone or extreme events, all of those things they talk about in 1 year during this time, extreme weather events in India for that particular duration from January 1st to September 30th of 2023. I think they are coming up with the every year report. So, you may be interested in downloading the future reports, and maybe you may find opportunities to work in those kinds of places if you have fancy ideas coming out of your research that you think you can help improve the understanding. So, the seasonal analysis is done for different seasons, winter, pre-monsoon, monsoon and post-monsoon. They come up with how many events that happened on a country scale here. So, I will kind of skip all this. So, they show on a map how many events that happened, like lightning for a given location, and they kind of total them up. For every event they say, like heat waves, extreme events, cold waves, snowfall, cloudburst, cyclones, right. And then they are establishing the connection there. In one of these reports they are talking about drought. They are connecting drought also to climate change, but in case of that Center for Environmental Science Analysis, they actually did not include drought, but I am assuming they might consider in the future, because shorter duration droughts are also possible still, they can consider. And you know, we are talking about extreme events for India. There are many ways that, you know, science can contribute to better understanding. This is another case study. I think Dr. Venkat Reddy talked about it previously, these two watersheds for, you know, extreme indices, right, several indices that we calculated. We took that exercise further down by building a model to predict flooded areas. This is not a great you know, outcome yet, you know, because we have to really improve our modeling skills, connecting hydrology to hydraulics and come up with flood area inundation maps. So, the you know, the same watershed Nagavalli and Vamsadhara basin, and then we looked at what is the inundation depth. The data is very scarce, we do not have the data to validate this kind of models, but we kind of quickly came up with a framework to establish climate, I mean looking at hurricanes, how they move into this area from Bay of Bengal or tropical cyclones, and then we looked at increased rainfall, and we took 7 or 8 events of those rainfall events, translated that into flood hydrographs, used those flood hydrographs into HECRAS models to come up with flood inundation areas. We do not really still have flood inundation depth, I guess, but we were just showing what areas are affected, and then we extended this to say they can use this for real time forecasting through web interface here. They can also use some of the model outputs. I am not sure whether it is still live, but at that time when the project was going on for 3 years, we came up with this outcome. The next one I wanted to show you just as information in the last few minutes before we conclude is this Himalayan glacier. How many of you have heard of the Chamoli disaster that happened in 2021, February 7th of 2021? I know somebody is from IIT Roorkee. Did anybody hear that before? Have you heard of this incident? Okay, good. Yeah, so I think in one of the slides I will have, there is the huge glacier collapse that happened, yeah, here. You know, that glacier mass that suddenly collapsed, it's about, you know, 16,000 feet altitude, higher, you know, mountains, and it's close to China border. I visited this spot 3 years ago. It's about 9 hours from IIT Roorkee. We 17 people went there. We looked at how this collapse actually carried water in the Ganges, and it really flowed through this you know, all the tributaries, Rishi Ganga, Dhauli Ganga, and then through Vishnu Prayag area. It went to Joshimath, and the areas that we looked at, these are the places where we kind of flew drones, and we looked at how the, you know, this drone we were flying, and then we kind of used the segments to calculate flood inundation areas. I mean, used hydrology models, and Tapovan is the hydropower plant that got destroyed. Some 75 to 100 people died in this particular site also. It's an extreme event analysis. I am just showing this as a case study that I did, but I did not finish this analysis. This is something that one can take up further to really look at how to quantify what was the loss of ice mass or glacier mass that we had from that uphill portion, and how it got carried, how it moved through the system, and then it did not go further down. I think the energy got dissipated downstream, it did not really propagate further down after Joshimath or somewhere, or maybe they stopped the flow, but the water height went so high that it even removed some of the bridges, strong bridges, and I took some pictures also. I don't know whether I have them now, but I will show at some point. But it's a fascinating place. There is science to be done in this case. We kind of did the limited analysis using SWOT model, which is not an event model, but we went ahead and used. We came up with, you know, converting rainfall into runoff, and then that is an event model, right? I mean, it happened in few hours. So we are just using hydrology model to understand what is the average annual rainfall or precipitation to runoff relationship. So the main idea here is to introduce you to the concept of you know, extreme events in today's class. I will actually show you a little more about climate. I mean, I'll introduce the idea of the last few minutes or first few minutes of tomorrow's class talking about the connection between climate variability and climate change. But I just want to provoke your thoughts right now. Can somebody tell me what is the difference? What is climate variability and what is climate change? You know, as a faculty. Very good. Yeah, that is the point. Climate variability is talking about a longer time period, and again it is also talking a little bit about the past conditions. Climate change is primarily related in the context of future. It is also longer term projections, but climate change in the context, people normally talk about future conditions. And of course, precipitation, evapotranspiration, interception, soil moisture, groundwater storage and stream flow is the driving force, as we know, in hydroclimatology, and they provide the connection to water resources management. And if you look at the time steps here, this is an important one: days, months, years, decades and centuries. Climate change looks at century scale. Climate variability looks at decades to multiple years. Seasons are generally in months, days are weather events. So, we are talking, your discussion this morning was centered around weather, but we kind of looked at seasons to climate variability and climate change in the last 2 days of lecture, generally talking about what happened in the last 100 years, what happens in the next 100 years, you know, for a given region, and specific events that we looked at. And you know, it can happen in days, seconds to minutes to hours to days, weather events, and in many cases some of these disasters that happens on a climate scale. So, a kind of a nice illustration and saying the connection between or the distinction between climate variability and climate change. I will stop here, but I think we are very close to kind of wrapping up this text and then talking about land atmospheric interaction and how it leads to flooding discussions. I think that is the connection that we can easily go from here to tomorrow's class. Before we close for today, is there any burning question or sticky point that you have in your mind that you want to clarify now? If not, certainly up to this point, whatever is presented, we will post the material of these slides as well as the PDF of the documents that I extracted these graphs and reports from, that you can keep for your reference. You do not need to read them thoroughly now, but at least when you go back, if you want to kind of refresh your memory and relate to what you are doing or pursue something different from what is done already, those things can happen based on the discussions that we have here today as well as what we had discussed yesterday. I will stop here. Unless you have any questions, I think I do not want to stand in the middle between you and the lunch. So, we will. No SWOT model for this session, because I think we will have HMS event model, and we will have HEC-RAS, I assume, and then we will talk about machine learning models little bit on the last few days, because we did some neat stuff. Google Earth Engine based analysis also we will show you, land cover, land classification. I did some work on machine learning integrated flood forecasting. If anybody is interested, we can discuss that later on, but that is not part of this class anyway, not to go in that depth actually. Okay? All right, I will stop here. Okay, I hope you get some energy, some rest before coming back at 2:15. We will meet at the same place like yesterday and go from there. Okay? Okay.